Next, we'll continue our discussion of Chapter 3, Matter and Energy, and we'll discuss specific heat. I mentioned in a previous section of this chapter that temperature is one way to measure heat energy. Temperature does in fact relate to heat energy, but we need a proportionality constant in order to correctly relate energy to temperature. And that proportionality constant is called specific heat. In this chapter, we'll learn to use specific heat to calculate heat loss or heat gain. Specific heat, represented in this text as SH, but often in other texts as C sub S, is different for different substances and is specific to that substance. Specific heat is defined as the amount of heat required to raise the temperature of exactly 1 gram of a substance by exactly 1 degree C. Specific heat has units of joules per gram degree C in the international system and calories per gram per degree C in the metric system. So we see here that the specific heat for water is 1 calorie per gram per degree C and 4.184 joules per gram per degree C. Here are some specific heats of some common substances. We have aluminum at, well, let's look at the joules per gram degree C. Aluminum is 0.897, gold is 0.129, titanium 0.523. Let's look at water. Notice water is the highest on this list at 4.184 joules per gram per degree C. Water has a very high specific heat, and that's why coastal cities tend to be warmer than close inland cities. Let's have a learning check. When ocean water cools, the surrounding air cools, warms, or stays the same. Sand in the desert is hot in the day and cool at night. Sand must have a high or low specific heat. Let's check the answers. When ocean water cools, the surrounding air warms. This is because the ocean water releases heat to the air. That's why coastal cities tend to stay warmer. Sand in the desert is hot in the day and cool at night. This is because sand has a low specific heat. It can't hold on to the heat and it cools off very quickly. We can calculate the amount of heat gained or lost by a substance by measuring its mass and temperature change. Specific heat is the constant that we use to relate heat to mass and temperature change. The amount of heat gained or lost by a substance is dependent on the amount of substance that we have through the mass, and therefore it matters how much substance we have. The equation for heat gained or lost is given by Q is equal to M for mass times the specific heat, we'll call it SH, times delta T, which is the temperature change. Other books may write this as Q equals M C sub S for specific heat times delta T. Some people call this the MCAT equation. If you need the amount of heat in calories, you'll use the specific heat in calories per gram degree C. If you need it in joules, you'll use the specific heat, which has units of joules per gram degree C. What is the specific heat if 24.8 grams of a metal absorbs 275 joules of energy and the temperature rises from 20.2 to 24.5? Let's remember that delta T is equal to T sub F minus T sub I. In other words, the change in something is given by final minus initial. And our heat is equal to mass times specific heat times delta T. So we'll need to solve for the specific heat in order to calculate this. So let's rewrite our equation. Q is equal to M times SH times delta T. We need to get SH on a side by itself. In order to do that, we just need to divide by delta T and M. So Q divided by delta T times M is equal to SH. And we could just go ahead and rewrite this as SH is equal to Q divided by delta T times M. Let's go ahead and erase the information that we don't need. And then we can perform the calculation. All right, SH is equal to Q, which we were given as 275 joules. Now let's remember that our specific heat should be in joules per gram per degree C, and therefore we don't need to perform a conversion there. All right, divided by delta T, we can go ahead and just put that in 24.5 degrees C minus 20.2 degrees C. And we'll just put that in parentheses because we'll need to perform that first before we multiply times the mass. The mass of our substance is 24.8 grams. Now this will give us units of joules per gram degree C, and that will be correct. So in order to perform the calculation and find the specific heat, we take 24.5 and subtract 20.2 from it. Now let's go ahead and do that, and then we'll perform the final calculation. 24.5 minus 20.2 is equal to 4.3 degrees C. So the specific heat, let's just change colors so we won't get mixed up here. So specific heat is equal to 275 joules divided by 4.3 degrees C times 24.8 grams. So that's equal to 2.6 joules per gram degrees C. We're limited to two significant figures here because when we subtract 20.2 from 24.5, we actually lose a significant figure. Because remember, when we're adding and subtracting, we're limited to the number of decimal places. And we have one decimal place here. Therefore, our answer when we subtract will be 4.3 degrees C. So when we rewrite our problem as we did in the green portion, we have 275 divided by 4.3 times 24.8. Notice that the 4.3 has two significant figures. The 24.8 has 3, and the 275 has 3. When multiplying and dividing, we're limited to the least number of significant figures, and therefore we'll be limited to 2 in our final answer, which gives us 2.6 joules per gram per degree C.